Welcome back to R for Economics. In this video, we'll be talking about decision trees. So first we need to bring in a bunch of libraries. Some of these libraries are just for bringing a data set. R sample does data splitting, and Ames housing is the data set that we'll use for the regression for one of the estimations. So first we look at the spam data set. So this is spam emails, and it's a categorical data set. We set a seed because I want this to be repeatable for you. So we bring in our data, spam7. We can rename it as my data to make sure that it's in a format that we're able to reuse. We can see that it's got some control totals, dollar, if it mentions dollar, if it mentions bang, money, so on. And then a yes, no, indicating whether it's spam or not. So we have a large data set. As you can see, there's close to 4,000 observations, or over 4,600 observations. Now, the first thing we want to do is generate a set, and we can use sample as a function, which will allow us to split the sample based on 1 or 2. Now that it's identified and randomly generated an ordering of 1 or 2. We can split our data set into a training and then a testing. And what we want to do is train the model using the trained data set and then test it to see how well it does predicting our test data set. So we could, if we need to, we could look at these properties, but they're very similar to my data because it is a random draw. So first thing we do is decision tree, and this is rpart. And as you can see, it's got 2,305 observations, and it's splitting on dollar, and then bang on one branch, and then controlled total on a third branch. And then you can see that the other split to the dollar at 2 goes directly here. And then you can see that it seems to indicate that yes is preferred here, and no is preferred in this one with the stronger results. So let's have a look at the plot for this, and we can see that the split here, and this is our decision tree, is that if the dollar value is more than 0.056, then we want to go directly to yes, this is a spam. But if it's less than that, then it's into the no. And then it goes to bang and decides to split down to no. And then this one's a yes. And then it splits it again with control, saying we can further divide this down. Okay, we can look at the summary for this. And this is a fairly long list of items. We can print the important things, which is showing what the kind of nodes and what kind of error we're getting if we have no splits, 1 split, and then the 3 splits. And here are the 3 splits, dollar, bang, and control. We can plot these, and we can see that as you split more and more, you can see that the error rate is going down relative. So now let's get back to our prediction, which is the ultimate goal of these types of approaches. So we're going to predict. We're going to then define this, because this will be values probably seven. We can see that this is split between 0 and 1, and 1s indicate that this is a yes, so above 0.5 will be a yes, and below will be a no. So we can redefine this as a binary pairing of yes, no's, and do the same thing for our spam test, our known data from our test data set. And then we can generate a correlation matrix where if they're both 1s, then you're going to get a value. If they're both no's, then you'll get a value. And then if you get yes and no and yes. So here we can see on the main diagonal that we're accounting for about 85% of the the variation, or we're correctly classifying it. And then on the off diagonal here and here, we can sum those up and we see we get 0.146, which is the misclassification rate. So 14.6% misclassified. Now, an alternative approach is to use the C-tree. C-tree does the same thing. It has similar things, but it does much more breaks. Okay, it gives you a little bit more control, and you might want to restrict the number of breaks and maybe move these around. But it gives you a chance to make more specific detailed observations and detailed discriminations between the variables. We can plot this, and we can see that it looks absolutely nearly impossible to read. We can see that the summary is just an output. We'd have to look at each of these. But we can still do predictions. We can still define these things as yes and no's, as we did before. And we can get the same kind of matrix that we had up here. So now we can see that we've improved our yes, yes, and improved our no, no's. And then the off diagonal seems to have improved a little bit. Previously, it was 14.1, and now with this new one, it's now 0.133, so we're 13.3% misclassified. So we've done an improvement by doing a much larger tree with much more detail. Now, let's go on to a regression version of this. So this was a classification, say yes, no, or a set of observations. Now we're going to look at regression. So we'll set the seed so that it's reproducible, and we can use the initial split function. And now we can make an Ames train and an Ames test data set. And these are just subsets of the main one. And the thing is, it's now 70% is training, and then the other 30% is going to be testing. This is a large data set. So now we can use rpart, and the thing we want to do is find the formula for the sale price based on all the other data in the Ames training set. So if we do a summary of Ames test, we can see that there's approximately 80 other variables in this entire data set that could be used to examine this. So we're going to run the rpart, and we can see that the tree is very involved. It doesn't go that deep, but it is fairly involved. And then when we plot this, we can see the type of model that we're going to get. And it's the same decision type tree where we're moving over on this way, it's getting larger, and over on this side, it's getting smaller. The values that we're trying to regress, the sales price. We can get summary, where we can look at all the information that we had before. We can get CP, which tells us that as we increase our splits, our errors start to drop. The relative error starts to improve all the way through. And we can plot this relative error here. And we can see that we get a lot initially, and then this, once we get down to here, 4 or 5 splits is probably more than enough. Again, we can predict, and we can get a summary of that prediction. We can get a summary of what the true values were for the test. And then we can get a plot of these. And note that the test price, the true values, are on the vertical axes. And a decision tree will give you discrete boxes to put things in. And this is where the split is occurring, and this is a value that it's giving the sale price. So you can see that it's very jagged. But this doesn't limit us from getting a root mean squared error of 39,852. Alternatively, as we had before, we have our C tree where we can do the same approach, and you can see that this is much larger tree. If we try to do the summary of this, it's going to give that again. If we try to plot this thing, we can see that it's unreadable, but it's going to have much more detail because it's trying to use as much information as possible. We can get our predictions. We can do the summary of our predictions. We can see that it looks kind of similar to what we had before. We can plot these things, and because there are more breaks and branches in the tree, in the decision tree, then we can see that we get more discrete boxes to be able to put observations in. And then we get our root mean squared error, and we can see that we've improved from our 39,000, and we're now at 33,000. So having a larger tree will improve your estimates in this case, but this is at the risk of having cases like here where we have one observation as an outcome. So you're going to increase or lose on your variance. Okay, great, and we'll see you in the next video.